So today I want to talk about a concept that is a little bit outside the kind of like, generative mainstream. Certainly it's one of these topics that you're going to hear about if you encounter generative models, but I will say that for the purposes of things like image generation and so on, that it's not necessarily going to be the go-to method. But I want to talk about it because I think it's kind of cool. So today's topic is what's called normalizing flow models. And part of the reason that I like it is because I think it has ties back to probability. Like if you took probability, hopefully you did, and also just like kind of fundamental calculus, changes of variables and stuff like that, right? So all the stuff we've been talking about so far is really about finding a way to sample from the distribution of the data that we show the model, right? So VAEs, GANs, all that stuff, VAEs, GANs, generative models in general. All these things are about, ways to easily sample from a kind of very underlying, complicated probability distribution P of x, right? So for example, if I was going to ask you to describe the true probability distribution of pictures of cats, right, that would be extremely difficult to describe in pixel space. But if I build a GAN and I say, okay, now I'm just going to feed the GAN with random noise and I sample a picture of a cat, that makes it suddenly super easy to sample from the space of cats, right? So the way this generally works on everything we've talked about so far is, basically we introduce some latent variable, z, that's easy to sample. And then we push that through some network, right? And this could be, whatever we want, to produce basically a sample of x that hopefully follows the underlying probability distribution of x, right? And so when I teach probability, one of the things we talk about is, how do I sample from a arbitrary probability distribution, right? So hopefully this is a kind of a familiar idea. So the related idea from probability is, I don't know why I can't get this paper off the page. So it's kind of related to sampling from general PDF, right? So if I gave you a kind of one-dimensional PDF and I asked you to generate a sample from this distribution, right? The kind of standard way to do it is to take the PDF. So if this is my PDF of x, I create the cumulative density function, capital F. This is called the CDF of x, right? That's a function that monotonically increases from 0 to eventually up to 1, right? And then the easiest way to do it is to say, okay, now I'm going to take a sample u, which is distributed on the interval 0 to 1, right? I basically generate some random number here. I follow that over onto the CDF, and then I create a sample x, right? And so the idea is that, maybe actually it would be better to call this z to kind of keep it in the theme of latents, right? So if I sample my z uniform on 0, 1, then I get a sample in x that is distributed according to this PDF, right? So the idea is that x, which is kind of like saying I take the inverse CDF of z, follows the PDF little f of x. Just a quick show of hands. Does this sound familiar to anybody who took probability? For me, this is like towards the last lecture of probability, but still. All right. Well, if you didn't know it, now you know, right? But the problem with this technique is that generally, for many PDFs, number one, the CDF is not invertible, right? So the problematic part is that, for example, I can't generate Gaussian random variables in this way, right? Because the Gaussian CDF is a complicated thing that I have to look up a table. If you remember Q tables from probabilities, at least you should remember those Q tables, right? That's like a numerical way of getting samples of the Gaussian, PDF, right? And so part of the problem is that the Gaussian CDF is not analytical, or not, easy to write down. So the problem is that for many PDFs, the CDF isn't invertible, which is kind of what I need, right? Because here I'm taking the inverse CDF of Z. Or we may not even have an expression for the CDF, right? So normalizing flow models are a clever way of getting around this issue of invertibility in a neat way. And so, like I said, while they are not like the first choice for generating like super high quality, synthetic images of faces or whatnot, they will still do the job and they still look pretty good. And I think it's also kind of a neat, novel application of math that if you took probability and calculus, you should already know, okay? And so let's kind of set up our notation, right? So the idea is to, let me say here, so normalizing flow models are a kind of clever way of getting around this for, neural networks. Okay. Man, my writing is getting worse. I have to do better. Okay, so here's the idea. Kind of same setup as usual. We have X, should have this desired distribution, which let's call the PDF P of X, okay? And let Z be some simple distribution like our Gaussians, right? Okay. So what I'm going to do is I'm going to make a mapping between X and Z that is explicitly easy to invert, okay? So we will create an invertible mapping that is f of x equals z and g of z equals x, where g is equal to f inverse. And then we're going to use the chain rule and Jacobians to find an exact and tractable formula for this distribution f of x, or this distribution p of x, right? So we'll arrive at an exact tractable formula for this distribution that we want. Okay. Now, you should already know kind of how to do this a little bit from way back in changes of variables of calculus, right? So think about, for example, Cartesian to polar conversion, right? So, one thing to remember is like change of variables. One of the first things that we talk about in like 2D calculus. So, if I want to change from coordinates like x comma y two coordinates, r comma theta, I have a formula that goes back and forth between these things, right? So I know that x equals r cosine theta and y equals r sine theta. And the same way, I can find the formulas for r and theta in terms of x and y, right? So if I want to do an integral dx dy, right? So if I do some integral, double integral dx dy, I want to know how does that correspond to some integral dr d theta, right? Hopefully you remember from calculus that when we do this conversion, I convert all my x's and y's into r's and thetas, but then I have this special r, right? Dx dy I know corresponds to r dr d theta, right? Where did that r come from, right? So the r came from the mapping between xy and r theta via something called the Jacobian, okay? So this r, if we remember from calculus, kind of comes from a determinant, right? I have a determinant that's like I take the partial x with respect to r, partial x with respect to theta, partial y with respect to r, partial y with respect to theta, right? If I look at my formula, this is like saying the derivative of this with respect to r is, cosine theta. Derivative with respect to theta is minus r sine theta. Then I have sine theta and r cosine theta. When I take the determinant of this, I get basically r cosine squared theta plus r sine squared theta, and that gives me the r, right? And so this thing is called the Jacobian, or the Jacobian determinant, and it tells us basically the scaling factor that I need to do to go from dx dy in some location to dr d theta in some other location. It's kind of saying if I take an infinitesimally small little squared dx dy, what kind of infinitesimally small square dr d theta do I need to make that conversion work, right? And so we use the very same intuition if I'm changing variables in the context of a probability density function, right? So for example, same kind of idea for, changing variables in a PDF, right? So suppose I had a density that was defined in x and y space, and I wanted to turn into a PDF in r and theta space. I should be able to do that, but I have to do more than just use the formulas that go from r theta to xy. I also need to have this Jacobian, right? So for example, if I had basically old variables z1, z2, and I'm turning them into new variables x1, x2, and I have the PDF in z, I kind of want to know what is the PDF going to be in x. It seems like it should be pretty related, and it is, right? The PDF in x is just the PDF in z. Now remember that this z here, back in my slides a couple times ago, this z I'm thinking about like a function of x, right? So really it's like saying I have a function of x that I plug in to get z. I plug in that function of x into the PDF of z. That will give me some equation in terms of x1, x2, but I need more than that. I need to multiply that by the absolute value of the determinant of this matrix, which is just the Jacobian again. And the reason I take the absolute value is because PDFs always have to be positive, right? So I can't have a change of variables and then wind up with some PDF values that have negative numbers in them. That would be bad, right? The relative change in area or change in volume is always a positive value, right? So this is kind of like the central idea of changing variables. Yes, question?
Okay, so couldn't you also say that the PDF of X to the PDF of Z is isomorphic because of the previous defined definition? And then from that, couldn't you just say it's a linear transformation?
Well, so this is definitely not a linear transformation, right?
Yeah.
Because of the cosines and the sines, right? So I could have some nonlinear transformation. So one way to think about this is that, suppose that I amplified everything by some constant, right? Then I would have that scale factor coming out in the Jacobian, right? So like if everything was 2 times as big, then I'd have like a half or something coming into the Jacobian, right? And then when things are nonlinear, then that constant turns into something that depends on the actual variables themselves, right? Like, yeah. So, yeah, and I'm a little bit hazy or hesitant to use the word isomorphic, right? That's not quite the right word here, right? I mean, certainly things get more complicated if you can have like many-to-one mappings between the X world and the Z world. Like here, for example, this is good because it's a 1-to-1 mapping between X and Z, right? If it was like a many-to-one mapping in some direction, then life would be even worse, right? So like you'd probably have, and we did some, at least when I do probability, I do some examples like this, right? Where suddenly you have like multiple regions of the X world that are mapping into the same place in the Z world, right? And what is the corresponding PDF of Z, right?
Okay, so they're not necessarily isomorphic.
Right, so for the moment, let's assume, well, for everything has to be invertible, I'm assuming it's a 1-to-1 transformation, right? So for sure it's a 1-to-1 mapping, right? That's the key phrase, right? It's a bijection, right? Meaning that there's one variable goes to one variable, right? Yeah. Yeah, isomorphic, I don't think it's quite the right word for what we're talking about, though. Yeah.
Because it is bijective, but I don't know if it's surjective as well.
It is surjective.
That would make it isomorphic.
No, man, you're using all these big words. I mean, bijective means it goes both ways, right? But I don't think that, so to me, well, I'd have to actually, instead of talking out my butt, let's just do a quick Google of what exactly isomorphic means in this context. For PDFs, that's not a word I'm used to using in PDF world. I think about like graphs.
I mean, I'm just presuming that it's just a mapping.
Yeah, it's just a mapping. Yeah, it's a 1-to-1 mapping. Yeah. Okay. Other questions or comments? All right, so let's think about this in the context of computation and neural networks and so on, right? So this involves a determinant. And so one thing that we try to drill into you in like linear algebra is that, when at all possible, you should avoid explicitly computing determinants because they are computationally complex, right? So for example, when you take the inverse of a matrix, you could form it using, the, pivots and Gaussian elimination, all that stuff. You can actually form the inverse, but doing that is like an n-cubed operation, right? There are ways of solving linear algebra problems that don't require you to explicitly form the inverse, right? So we try to avoid taking that kind of determinant. So in general, issues are that, taking the determinant is an n-cubed operation. And like you were saying, in this case, the dimensionality of X and Z are the same, right? So it's like saying, okay, well, if I had if I'm trying to make a generative model for something that's like 1,000 dimensions long, then my Z is also 1,000 dimensions long, and my matrix I have to invert is 1,000 by 1,000, which will cost me 1,000 cubed operations, right? Which is not great. And so, we generally try to avoid doing that, right? So for example, even like a 32 by 32 image, if we think about it, is already 1,000 dimensional, which is really not great. Another thing that's not so great is that if I think about this in the world of neural networks, right? So our model so far has been that Z is some easy to sample thing like a Gaussian. I put it through some sort of complicated neural network, and then I produce X, right? So like, for example, think about a VAE, right? So, this here is kind of like the encoder part of an autoencoder, and then this thing here is like the decoder part of an autoencoder. And these could be like super complicated neural networks, right? That may not be possible to actually take derivatives of easily. And also, in practice, they may not even be invertible, right? Or not, they might not be inverse pairs of each other, right? So for example, there's no guarantee that in a VAE, the F part and the G part are related to each other at all, because they're kind of trained as separate networks, right? So generally not even inverses of each other. So what is the clever idea behind normalizing flows? So the key idea that we're going to introduce here is a clever way of iteratively changing from z to x by easy transformations that are super easy to compute the Jacobians for. Okay? So we're not actually stuck with this computational load of computing inverses. And also, we're going to keep everything very explicitly invertible all along the line. Okay? So here's the key idea. So the clever idea that was started this whole area off was proposed by Din et al. In 2017. And the paper was called Real NVP, which stood for Real Valued Non-Volume Preserving Transformations. Okay? And so here's the key idea. What we do is we introduce a new kind of neural network layer, and this is called a coupling layer. Okay? So we have a new layer, new neural network layer called a coupling layer. And what this network does is it basically produces a scale factor and a translation value for each element of its input. Okay? So it's like saying I have some input comes in, it goes through a coupling layer, and what comes out are two other vectors, s and t, that are the same size as the input. Okay? So it's basically producing like a scale value and a translation vector. Okay, so now what we're going to do is I'm going to use the S and T that come out of this coupling layer to build a simple transformation to go from x to z or vice versa, right? So what I'm going to use is to say, okay, suppose I want to produce the latent z from the input x. So what I do is I first split the input in half. Okay, so let's suppose that my input, I'm just going to split down the line. If I have 100 elements, this is going to be 50, this is going to be 50. And then I pass x1 part through the coupling layer, or through a coupling layer, to get a scale vector, or a scale vector and a translation vector for that half. And then I'm going to make a translation or transformation that says, okay, z1 is going to be x1, z2 is going to be e to the scale factor, just element by element multiplied with x2 plus this translation. So here, this is just element by element multiplication. So what I'm going to get in this process is the z1 part is going to be exactly passing through the first half of x1. The z2 part is going to be transforming based on both x1 and x2, right? It's basically multiplying x2 by a scale factor and a translation that depend on this x1. And that S&T is some sort of complicated neural network, right? I don't have to necessarily know what's going on to produce this, but once I get the output of that coupling layer, this is how it manipulates to form the latent, okay? And I can observe that this is easy to undo, right? So if I wanted to get back to x1, x2, this is easy to invert. That is, x1 is just z1. x2 is, I have to subtract off the translation, and then I have to do element by element manipulation the other way. So I take e to the minus s of x1 times z2 minus the translation. So this is definitely not a linear operation at heart, because the neural network part of obtaining S and T is definitely not linear, right? It's got ReLUs and thresholds and stuff like that. But if I was given S and T, it would be easy to do this inversion, right? So far, it seems like this. I've still got a big neural network here, so how is this making life any easier, right? So the easier part is, again, if I want to look at the relationship between the distribution of these variables and the distribution of these variables, I go back to my formula, right? Again, I assume that if this is a latent variable, I know this. What I need to do is now compute this thing, right? I need to compute this complicated derivative. But the way I've set up the transformation makes that Jacobian very easy to compute, right? Let's think about what that is, right? So what I need to do is to compute, we need this j, which is like the partial of z with respect to x, partial of z1 with respect to x1, partial of z1 with respect to x2, partial of z2 with respect to x1, partial of z2 with respect to x2, right? So what would that be? I guess I've got the wrong part here. I have to look at this, right? So here, this is actually not that hard, right? So the partial of z1 with respect to x1 is just the identity matrix, right? It's like a identity matrix that is half the size of the original length of the signal, right? Z1 partial with respect to x2 is 0, right? Because z1 doesn't depend on x2 at all, right? So this is just going to be 0. Z2, taking the derivative with respect to x1, is going to be a huge mess, right? Because it depends on x1 via this coupling layer, this neural network that I don't necessarily easily able to model, right? So let's just call this mess. It's going to be some, in general, dense matrix. Like, again, if these are 100 by 100 variables, it's going to be like a dense 50 by 50 matrix, right? And then what is z2 derivative with respect to x2? Well, again, since this is element by element manipulation, all that's happening is that this translation goes away because there's no x2s here. And then all I'm doing is I'm going to pick off the corresponding element that multiplies each of the parts of x2. So this is going to be like basically a diagonal matrix that has values along the diagonal e to the s of x1, right? Because z2 is really just a scaled version of x2 multiplied by some scaling factor that may be complicated, but if I'm just taking the derivative, it's just going to be that constant coming off, right? So if I think about kind of like what the matrix looks like, it looks like 1, 1, 1, 1, 0 up here, a bunch of crud down here I don't care about, and then a bunch, I should probably not write zeros, and then a bunch of dots along the diagonal, right? This is all 0, this is all 0, this is all 0, this is all 0. So I end up with basically what's called a triangular matrix, right? I know. All right, there you go. So I end up with this kind of triangular matrix. In this case, this is what's called a lower triangular matrix. And the key thing is that hopefully, if you remember from your Gaussian elimination days, that it's very easy to take the determinant of a triangular matrix. All I do is I multiply the diagonal elements, right? So I don't care what this crap is down in the lower left-hand corner because it doesn't play into the value of the determinant. And so the cool thing is that now the determinant of j is just a product of a bunch of ones and the product of a bunch of numbers, which are these values here, which I already know, right? So the kind of clever thing is that the determinant of this J matrix is nothing more than the product of the values of this, e of the scaling factors. And, if I'm multiplying a bunch of these numbers up, I could just say this is like e to the sum of these scaling factors, right? Because that's the way the exponential thing works. So what we've learned is I made a complicated transformation that is mediated by this neural network coupling layer that produces this set of S's and T's. But I've also made an invertible transformation that is got a very easy Jacobian to compute, right? So after one step of this, I've transformed the Z's into some X's in a pretty complicated nonlinear way, but I can exactly evaluate what the PDF of the X is going to be, right? The PDF of X is just kind of like taking the PDF of Z that I know, subbing in the X part of the, inside the parentheses, and then multiplying by this single number that's a product of a bunch of easy things that come out of the network, right? So in this way, I have made one step of nonlinearity changing from Z to X, and that's cool, right? But one thing that you notice is I didn't touch half of my X's, right? So basically, note, I didn't touch the second half of, X, right? That is, or maybe I should say I didn't touch the first half of X, right? This X1 part just passed right through the network, right? But that's not a problem, right? Because all I can do is I can introduce another coupling layer where instead of, manipulating the second half of the vector, I now manipulate the first half, right? So the idea is that, no issue. On the next layer, I just switch which half of the vector is manipulated. Right? So it's like saying, first I take, kind of like x1 and x2. I put it through this coupling layer. Then I'm going to do something where x1 stays the same, and now this part has been manipulated, right? Then I'm going to put this through another coupling layer, except I'm going to apply the coupling layer to, this part of the vector. And now I'm going to manipulate it so that this part stays the same, and now this part gets transformed, right? And then if I wanted to, I could keep on doing that, right? I could then apply the coupling layer again, where this part stays the same, and now this part changes, right? So I can kind of keep on doing this incrementally, just choosing which half of the data I'm going to manipulate. And in that way, I can make some sort of very complicated nonlinear transformation that mixes up, that depends on all of the values of x in a way that's, kind of hard to, well, everything gets touched is kind of what I'm trying to say, right? So it's not like any part of x is sailing through to produce z, right? And then at every step of this, to figure out what is the overall composite Jacobian of this combined process, it's very easy, right? So at this point, this is like saying, you know, it's easy to look at the composition of the two layers by saying, you know, I have like F2 of F1 of X. You know, the Jacobian is just going to be the product of, you know, the J2 part and the J1 part, right? Both of which are easy things to compute, because each of these is a different lower triangular matrix that's easy to do. So the whole thing is very slick. Yeah?
Okay, so going back to the Hessian, couldn't you take the coupling layer of both x1 and x2 inverted and then get the result of both instead of...
So the reason that I want to leave one alone is so I can do this clever triangular matrix, right? That's the whole point, is that I don't want to make the computation of this determinant hard, right? Which means I'm willing to allow part of this matrix to be crappy, but I don't want to make the whole matrix crappy. That's why I do it in halves. And that's in some sense the key insight of what this paper was, is to say, you know, doing a whole transformation at once would mean that this determinant would be generally hard to compute, right? Doing it in a way that makes the transformation result in a triangular Jacobian makes this determinant super easy to compute, right? That was the kind of clever idea. And it's still like a fairly complicated function because this S comes out of a neural network, right? So that was, I thought that was a pretty clever approach in the first place, right? And so just in a way that you have a choice when you're building a neural network to decide how many layers you want, you can do this mixing and matching, you know, swapping as much as you want, right? Like you keep on doing it to build a more and more complicated, you know, swapping thing. And there is definitely some work on like, what is the right way? I think that there was one paper that suggested that instead of, you know, doing the top part and the bottom half of the data, you could also imagine that I could take like a, you know, checkerboard, and I could do half of the data like this on one pass, and then the other half of the checkers on the other pass. As long as I'm doing half and half, that Jacobian will still be okay, because basically, you know, you can think about this kind of like a permutation of the elements of X, and the permutation has determinant 1 as it goes, right? So if I think about take X, permute the elements, do something to half of it, you know, all that stuff is still going to be like an easily composable, easy to compute Jacobian, right? So this is kind of like, you know, a permutation also has this Jacobian determinant equal to 1, just because I'm not changing the sizes of anything. All I'm doing is flipping which indices I have, right? So basically, now we just train the network. And what's happening in training is that, you know, I have, you know, what I'm going to do is I'm going to tune the architecture and the elements of the S and the T coupling layer networks. And what I want to do is I want to minimize the log likelihood of the data given the model, right? So I want to basically minimize this log likelihood, which is related to the PDF of Z, which I know because I am specifying this, minus, you know, the log likelihood of the Jacobian is just the determinant of this thing, which is easy to compute by the way that I set it up, right? So kind of what I'm thinking about is that the target output of the forward network, Z equals f of x, is Gaussian. So this was the kind of idea, and when they applied this idea, they did it on kind of basic kind of data. So here's a 2D example to kind of illustrate. So here the idea is, suppose this is the target distribution that I want, right? This kind of weird two-piece curvy distribution. I want to be able to generate this distribution via sampling from a simple like Gaussian distribution, okay? So I build the network with, in this case, looks like 5 coupling layers. And again, I can specify what I want to have each coupling layer be like. This is like a neural network in itself, right? And then you can see here, there is a part where I am splitting things in half and kind of flipping around. Here's where I'm taking like the E, the S times things plus the translation. It's a very simple network to set up and train. And so, blah, blah, blah. You can see that in the early days, if I'm thinking about pushing f of x into the latent space, what I'm trying to do is I'm trying to get this set of red points here to look like kind of a Gaussian point cloud around the origin. And conversely, I have a latent space, which is like kind of Gaussian distributed points in the Z world. When I push it forward with the other part, the invertible part, I want to make it look like the two moons. And so as I train, every once in a while I kind of check in to see how these things are looking. And as I go further and further, eventually, at the very end of the notebook, this is kind of where I got to, right? So the forward mapping from the data space looks like something that is Gaussian-ish. I mean, it's not perfect, right? But it looks kind of like a blob. And then if I think about taking the Gaussian random variables, which are the green dots, and pushing them into like the X world, I get these kind of half-moon things that are pretty close to my original distribution, right? That's kind of the idea. And of course, this is just like a total toy example. But it was shown that then I could use this thing to do basically generative synthesis of, for example, face images, right? So the idea was from this simple model, this was extended by a paper called GLOW. And this was, again, some OpenAI and Google AI people, so Kingma and Darawal. This was NeurIPS 18. And then this basically created good quality RGB generative images of faces. I didn't put the faces in my PowerPoint presentation because by now we've seen a lot of generative faces that all look pretty much like faces. But the generated samples look pretty good. And so I like this method, and in kind of reading forward to the methods I want to teach you about for the rest of the class, I didn't come up with too many normalizing flow models, although there is one that I came across this weekend related to generating 3D samples. So that's one of the reasons I wanted to talk about it. So, kind of like the pros are that, everything is kind of like, easy to set up. Everything is invertible. The computational cost is generally low. On the other hand, this doesn't really, lend itself to kind of the cool stuff that we were doing with GANs and VAEs, for example, where I can kind of explore directions of the latent space that correspond to different attributes and so on. So I would say that the latent variables are not as easy to manipulate or interpret. And kind of at the same time, I would say that the image quality is not necessarily as good as you could get with a GAN, probably. But still, the fact that it works at all, I think, is a kind of a cool idea for dealing with complicated distributions. I mean, we're using it in some of our own research, right? Just because it's such an easy thing and a clever way of thinking about problems, right? And I think it's also good as an exercise of remembering like probability and changes of variables and so on, right? Except in the context of neural networks. So this is covered in one chapter of the Foster book, chapter 6. In some sense, this is the last of the major generative techniques that I want to talk about before we start talking about kind of like all the cool language stuff and DALL-E and so on, right? But in terms of like the fundamental like generative engines, right? Pretty much anything that you're going to see, I think, is going to be a variation on VAEs, GANs, diffusion, normalizing flows. There is one chapter of the Foster book that I didn't talk about, which is more related to time series type data, right? So like, I'm not really going to talk in this class about like, a lot of autoregressive stuff and LSTMs and RNNs and stuff like that. You may have seen those in other classes, but for what I want to talk about, I didn't think that it was worth getting into because I don't think I'm going to talk about it enough later, right? But if you're curious about that, there are a couple chapters in the Foster book that I didn't cover that talk about that. Okay. That actually wasn't as short of a lecture as I thought it was going to be. So any comments or questions about this? It's a little bit of a side topic, but I think it's kind of fun to play with. Okay, so I'm going to stop the lecture.